Okay, so now I am going to present an important topic that we will use it in all of our calculation next codes that we will write. It's a sparse matrix calculation. So let me close all of these files and open finite element try 1, 3. If I run, you can see the electric potential and finite element solution, exact solution. So I am going to calculate the running time. So in the Matlab software, when you want to evaluate the running time of your code, you can use this syntax. Tick your code type, right? So you can evaluate how much is running time of your code. For example, this is my code, finite element, try 1, FEA, try 1. If I press enter, you can see these results. Now, if I write here, tick, talk, also I can see the elapsed time. That is 0.25 seconds. So this is good because number of nodes is equal to 3. What if I write here 50? Save, run. This is 0.3. This is also good, not much different. So if I write here 500, save and run. 0.3, the same. 5,000, save, run. 0.8, this is higher, right? So suppose I write here 50,000, save, run. So as you can see here, the running time is high in this case, right? So this is important when we are going to solve large problems. We have to increase number of elements. And as you can see here, if we write our finite element code in this way, this is really high. Actually, as you can see here, the code is running yet. So let me break this code. You can break the running code in the Matlab software by holding the control key and pressing the C key. So, right, we tried to run this code using 50,000 nodes, but we couldn't. So let me reduce and run the code again. So why we cannot run this code when number of nodes is high? The issue is here. When we allocate the memory using zeros function, actually we allocate this amount of memory, number of nodes times number of nodes for a stiffness matrix. And the stiffness matrix, each element of a stiffness matrix is a double, right? Is a double. The type is double. In MATLAB, you can show the type of the variable using this syntax. For example, if I write a equal to 5 and I write class of a as you can see, the class of A is double. So if I clear all variables and write A equal to 5 and write whose, as you can see, the class of A is double and we need to allocate 8 bytes of the memory. So when we construct the stiffness matrix using the zeros function, actually we allocate n times 8 bytes of the memory, right? This is really high. But we should use a sparse matrix because, as you know, most of elements of the stiffness matrix are equal to 0. So we don't need to do calculations for them or allocate memory, right? According to this equation that we have here. So as you can see, most of elements of this matrix are equal to 0. So how I can define sparse matrices in Matlab? If I write here A equal to 1, 2, 3, 5, 8, 6, 6, 3, and 1. So this is a full matrix, right? And now let's consider 3, 0 elements. So this is also a full matrix. And now if I write a sparse of A, so this is a sparse matrix. As you can see here, the way that Matlab shows the full matrix and a sparse matrix is different, right? This is full matrix, but this is a sparse matrix. We have the row index and column index and the value here, but here we have the exact format. So if I write here A equal to a sparse A, I can construct a sparse matrix, and using this command, I can change back to the full version, right? So if I write here A and write whose, full A and write whose, as you can see, the size of A is 3 by 3 and it allocates 72 bytes, right? Because 3 by 3 times 8 is 72 for all of its elements. Now, if I write this one and write whose, this is 1 to 8, right? So this is different. The way that Matlab stores a sparse matrix is different. So when the size of matrix is low, the memory related to the sparse matrix could be higher than normal matrix, but this number is really low when the size of matrix is high. So how we can define a sparse matrix in Matlab? For example, suppose I am going to define this matrix 1, 1, 0, and 2. So we should specify the index I and index j, or row index and column index of each element, and also corresponding values. For example, I should write something like this: index I, that is equal 1, 1, and 2, right? Or I can walk in this direction. This is 1, 2, 1, 2, but this is 0, right? I don't want to store this one. So I should write something like this: 1, 2, 1. This is index I and index j is equal 1 and 2 and 2, right? So this is index of this element is 1, index of this element is 2, and this is 2. So this is direction of definition of this sparse matrix. So what is the value is 1, 1, and 2. The value, I write here val, is equal 1, 1, and 2. So now if I write a sparse of index I, index j, and value. So this is the sparse matrix, our sparse matrix. And if I write full version of A, you can see this matrix, right? That we're going to define it. So here, if I want to define this stiffness matrix, I can use this format. I can write here index I, index j, and value of k. So here you can see for each linear element, we have 4 non-zero value for the stiffness matrix, right? This is for linear mesh element. And for each linear mesh element, we have 4 non-zero elements, values. So I write something like this. Zeros of NE and 4. I allocate these matrices for index I, j, and value. And here I write something like this. Let me save. I write something like this. What is the index I and index j? Index I is corresponding to these values, rows, and index j is corresponding to these values. So I can write here something like this. Index I of element I is equal this. I can write connectivity list, something like this. So for example, this syntax is index programming. If I have A equal to 5, 6, 1, and 2, if I want to change the values of this column, I can use this syntax. All rows of the second matrix, change them to 8 and 9. So if I press enter, as you can see here, this is 8, this is 9, right? By this method, I can change the values of elements of each column of this matrix. This is really beautiful kind of programming. So this is 1, 1, 2, 2, 1, 1, 2, 2, and for index j, I can do the same. Index j 1, 2, 1, 2, 1, 2, 1, 2. And what is the value? What is the value? I write here value of k is equal this element and this. So this is negative, this is negative, and okay. So right, positive, negative, negative, positive. So here, as you can see, we define these three matrices different from the previous one, and we allocated only 3 times 4 times NE doubles from the memory. Now, here I can construct the K using this command, a sparse of index I, index J, and value. So the index I and index J is, excuse me, this is 4 by number of mesh elements. The number of rows is 4, and right. Now it is correct. This is delete index J. Save. So I use also this Matlab syntax. Actually, when we have a matrix in Matlab, we can vectorize it using this command. A point enter. So using this command, we can change a matrix to a vector, right? So this is a little bit tricky, but beautiful. You can read more about it in the Matlab help. So if I write here index I, index J, and value of K, so we vectorize those matrices, and now let's run the code using, for example, 2 elements. And now let's try 50,000. Run. Solved, right? Totally different from the previous one. So you can write here tick, tock, and right, 2.6 seconds, right? So this is really a big problem. We are solving a finite element problem considering 50,000 elements. That is really high. Now let's try. I write here 1 million, right? 1 million mesh elements. So let's try run to check if we can solve a problem with 1 million mesh elements or not. So if we can't solve this problem for one-dimensional, we can solve for corresponding two-dimensional and three-dimensional problems, right? So this is really a big calculation, 1 million mesh elements. Actually, if we want to use the previous method, we cannot solve this problem. But here, as you can see, the solution is in progress. The area error is round to 0, and we solved this problem. This is beautiful, right? Also, I can run it again to calculate the running time. And as you can see here, using a sparse matrix calculation and definition of the stiffness matrix in this way, we can solve a problem with 1 million mesh elements. As you can see here, this is thanks to Matlab sparse matrix calculations and this comment, right? That is really beautiful. And right, you can use the Matlab software for customized designs. And right, that is really good. It's equal to 47 seconds. So, yes. Yes. Okay. So, do you have any question?
No, it's clear.
Right.